In this course, we will be discussing several analytical tools and techniques that are useful in the analysis and design of communication systems. And in the previous lecture, we saw one such technique of representing a bandpass signal as a low-pass signal. So we did the bandpass to low-pass transformation in the previous lectures. And the idea was that it is easier to process lower frequencies. So therefore, the bandpass signal, which is at the higher frequencies, is transformed to a low-pass signal, which has lower frequency components. And that was an analytical technique, and we saw what happens as a result of that in the previous lecture. Now, in today's lecture, we are going to talk about representing signals in a geometric way as vectors in a multidimensional space. So the focus of today's lecture, and in fact of this lecture and maybe the next couple of lectures, is going to be on the geometric representation of signals, which is basically trying to represent the signals as vectors in an n-dimensional space. Now, the question is, how do we find the elements of those vectors, and what should be the axis, the axis of the space in which we are trying to represent the signals, and how do we find out those axes, what are the properties of the axis, and so on. So today we are going to start off with that discussion, and basically what we're trying to do is, suppose we have a set of signals. If we denote them as SI of t, so let's say we consider a set of signals. So we have considered a set of signals, that is M signals, which we denote as SI of t for I equals 1, 2, 3 up to M. So that's S1 of t, S2 of t, S3 of t up to Sm of t. So that's a set of M signals, and we want to represent them as vectors in an n-dimensional space. So the signals SI of t to be represented as vectors in an n-dimensional space where the dimension n is going to be less than or equal to m. So the number of dimensions in that space is going to be at most the number of signals, which is m. It can be less than m, but not more than m. So we are going to represent these set of signals in the n-dimensional space as vectors. So we can basically write the signals, which are normally depicted as functions of time SI of t, in terms of or they can be transformed as some vector, and we'll just simply call each signal in this vector representation as simply SI, as a column vector of length n. So SI will have the first element SI1, SI2, and so on up to SIN, because the dimensions of the space is going to be n, so it's going to be a vector of length n. So signal S1 of t will be denoted by a vector S1 as S11, S12, S13 up to S1n. Similarly, S2 of t will be denoted as a vector S2, as which has elements S21, S22, S23 up to S2n, and so on. So that is our vector representation of our signal, right? And basically, once we have this as a vector representation, we are going to have the axis of our space. So for example, if it's a two-dimensional space, okay, for n equals 2, for example, then we are going to have two axes, the x-axis and the y-axis sort of thing. But what is important is what what does that axis represent? So the axis represents what are called as the basis functions, and if n is equal to 2, then our signals, for example, Si of t will be represented as a vector Si, and because it's a two-dimensional space, it will be Si1, Si2. So each vector is of length 2 because there are two dimensions. Now the axis that we have here, for the two-dimensional case, we have two axes. If it's a three-dimensional space, then there will be three axes, and we can have any value for n as long as that n is less than or equal to m. Obviously, it's not possible to visualize n greater than 3 on a flat piece of paper or screen here. So, but mathematically that's possible. And the axes are called as the basis functions, which we denote as phi. So we call the axis as phi 1 of t and phi 2 of t. So the axis on which the axis in the space on which the signals are represented as vectors, those axes are called as the basis functions. So let me write that. So the axes are called basis functions. So basically we are going to write those signals in terms of the basis functions. And now for all this to be possible, okay, for us to be able to do all of this, there are a few conditions that must be satisfied. First, for the signals themselves that can be represented as vectors in an n-dimensional space, and also there are some conditions that the basis functions must also satisfy. And let's first talk about what is the condition that the signals must satisfy in order to be able to do this process. And that condition is that the signals must all be energy signals. So this is applicable for Si of t, which are energy signals. So Si of t should be energy signals. Okay. Now what do you mean by energy signals? You can refresh from your undergraduate. Okay, just read the text and you will find what is the meaning of energy signals. Okay, I won't go into that. So signals are usually classified as energy signals and power signals, so you can refresh yourself as to what exactly is meant by energy signals. And so that's the first condition, that the signals must satisfy for us to be able to represent them as vectors in an n-dimensional space. Now, what are the conditions or properties that the basis functions must satisfy in order to be able to do this process? So the properties that the basis functions must have are, the first property is that the basis functions should be orthogonal to each other. By orthogonal, we mean that the basis function should be perpendicular to each other, as we have seen here. Okay, their angle is 90 degrees, or in other words, putting it mathematically, it means that the dot product of the basis functions is 0. Okay, that is what we mean by orthogonal. And the second property of the basis functions is that the basis function should have unit energy. So the energy for each of the basis functions should be equal to 1. So a basis function which satisfies both these properties, that is of being orthogonal with respect to each other, and also each of them having unit energy, that is energy equal to 1, we call such basis functions as orthonormal basis functions. So these are called as orthonormal, that's orthonormal basis functions. Okay, so if it's an n-dimensional space, then we are going to have n basis functions, which we will denote as phi1 of t, phi2 of t, phi3 of t, and so on up to phi n of t. Now the n should be less than or equal to m, where m is the number of signals we have in our set of signals, which is si of t, for I going from 1 to m. So n should be less than or equal to m. Okay, so these are the properties of the basis functions. Now we'll see how we can go about the process of representing the signals in terms of the basis functions, and later on, and maybe in the next lecture and next lecture or two, we will also discuss how to compute those basis functions. How do we find this phi1 of t, phi2 of t? Now at this stage we will just assume that there is some phi1 of t and phi2 of t, and you will use the properties that they are orthogonal and that they have unit energy, and try to see how we can represent our signals as vectors in the n-dimensional space, represented by these basis functions as the axis in the space. Okay, later on we will see how to actually compute these basis functions as well. Now let's try to write these properties mathematically. What do we mean by the basis functions being orthogonal? Okay, if we take any phi I of t and phi j of t, if we take any two of these basis functions, they are orthogonal means that their dot product is 0. So that means if we write it as a dot product, let me write that orthogonal means that the dot product, that is phi I of t, the integral of phi I of t into phi j of t from some interval 0 to t dt is equal to 0 if I is not equal to j. Okay, so that means if we take I and j to be different numbers, so between phi 1 and phi 2 and phi 1 and phi 3, or phi 2 and phi 4, or phi 2 and phi 3, okay, the dot product will be 0 if I is not equal to 0, and it's equal to 1 if I is equal to j. That means if I is equal to j, that's the dot product of phi 1 of t with phi 1 of t. That will become the integral of phi 1 square of t, right? And that's equal to 1. And when it's equal to 1, that means it's having equal energy. If it is simply non-zero, any other number other than 0, then it is still orthogonal. But if it's equal to 1, it is not just orthogonal. If it satisfies this property, it is not just orthogonal, but it's also orthonormal, because it is the dot product is 0 when I is not equal to j, and when I is equal to j, it's exactly equal to 1. That's unit energy. Now, if it is any other number that is other than 1 and other than 0, for example 2 or 5, then we say that it is simply orthogonal but not having unit energy, right? So that is what we mean by orthogonal here. And similarly for unit energy, what we write is, so let me write that here, I'll keep it on the same page. Unit energy, that happens when I is equal to j. So that means integral 0 to t phi I of t into phi I of t. Okay, when I is equal to j, that becomes phi I square of t dt. Phi I square of t dt is equal to 1, and that's exactly what we have here. Okay, now if it's equal to 1, it satisfies this condition, that's when I equal to j, so it's unit energy. If it is any other number other than 1 and non-zero, then it is simply orthogonal but not orthonormal. Okay, so the basis function should be orthonormal. That means their dot product should be 0 and their energy should be equal to 1. Okay, so that's phi I square. That's the definition of energy. Okay, so the integral of the squared function over 0 to t over the duration of the function. That is called as the energy. And if it's equal to 1, we call it as the function having unit energy. Okay, so now we have defined what these properties mean. What is the meaning of orthogonal, and what is the meaning of unit energy, and thereby what is the meaning of orthonormal basis functions. Okay, now the next thing we are going to do is we are going to say that we are going to represent the signals Si of t using the basis functions phi 1 of t, phi 2 of 3, phi 3 of t, and so on up to phi n. Okay, so we have seen earlier how we can write each signal in terms of a vector where each vector is of length n, and the elements of the vector are defined as si1, si2, and so on. So we can write our signal Si of t in terms of this vector and the basis functions phi j of t, and that way we can basically synthesize our signal by using these vector elements and the basis functions. So let's see how we can write that. So we can write the signals in terms of their vectors Si and the basis functions phi j of t for j1 to n, and the number of signals is I1 to m. So basically what we're trying to say is we can represent each of these signals Si of t as the as in this form, as the summation of the vector elements Sij into phi j of t for j equals 1 to n, and we can do this for all the signals, that is for I equals 1, 2, and up to m. So we have m such signals. So basically what we are trying to say is we can multiply each element, or we can multiply each element of the vectors of the vector representation of the signal with the corresponding basis function. So if we go back to the previous slide, so we have Si1, Si2. Okay, so the second number here is representing the j, so it's Si1 into phi 1 plus Si2 into phi 2 plus Si3 into phi 3 plus Sin into phi n. That's what that summation is depicting here. So j goes from 1 to n. So basically what we're trying to say is we can write this signal Si of t as Si1 into phi 1 of t plus Si2 into phi 2 of t plus Si3 into phi 3 of t plus so on and so on up to Sin into phi n of t, because the last value for j is n, so Sin into phi n of t. So that will be for each Si of t. So if we had S1 of t, it will be S11 phi 1 of t plus S12 phi 2 of t plus S13 phi 3 of t, and so on. S2 of t will be S21 phi 1 of t, S22 phi 2 of t plus S23 phi 3 of t up to S2n phi n of t. So that is what the summation is saying, and so that way we can represent each of the signals in terms of their vector notation and the basis functions. So for signal number 1, so as I said just now, we can write S1 of t as S11 phi 1 of t plus S12 phi 2 of t plus so on and so forth up to S1n phi n of t. Similarly, we can express S2 of t as S21 phi 1 of t plus S22 phi 2 of t plus so on and so forth up to S2n phi n of t, and similarly we can do for S3, S4 and so on. Now these elements of SI, how do we get these numbers? Okay, the elements of the vector representation of the signal SI of t, how do we compute those elements? So basically what I'm saying here is, how do we find out the values of SI1, SI2, SI3 up to SIN? What is the definition for them? So the definition for the elements of the vector representation of the signals are defined as, so we have each signal SI of t denoted as a vector SI, which is equal to SI1, SI2 up to SIN. So that's our vector notation for the signal, where the elements of this vector are defined as where each Sij is defined as the dot product of the signal Si of t with each of the n basis functions. So Si1 is the dot product of the signal Si of t with the basis function phi 1 of t. So this is basically Si1 into phi 1 of t, and when we integrate that from 0 to t, that gives us the value of this Si1. Okay, so that is what we are trying to say. So Sij is defined as integral 0 to t Si of t into phi j of t dt. So this particular element Si1 is obtained by taking the dot product of this Si of t with phi 1 of t, and that would give us Si1. Similarly, if you want Si2, the dot product of Si of t with phi 2 of t gives us the value for Si2. So computing the dot products of the signal with each of the basis functions which form the axis, that gives us the values of these elements of the vectors. Or basically what we're trying to do here is, each of these Sij is nothing but the projection of the signal Si of t onto the basis functions phi j of t. So the dot product here simply means the projection of Si of t onto phi j of t. So S11 is the projection of S1 of t onto phi 1 of t. S12 will be the projection of S1 of t onto the basis function phi 2 of t, and so on and so forth. So basically these elements of the vectors are nothing but the projections of the signal onto the basis functions. So let me write that, where, so that is Sij is the projection of Si of t onto phi j of t. Okay, now what do we mean exactly by projection? We will see in just a little bit, where I'll be drawing a diagram to depict exactly what we mean by projection. Okay, so what you need to know, this is important. Okay, what do we mean by projection? So just to give you a quick example, if we had for signal number 1 S1 of t, and the elements of the vectors would be S11, S12 and so on. So for example, we can write S11 as integral 0 to t S1 of t into phi 1 of t dt. So that's the projection of S1 of t onto the basis function phi 1 of t. Similarly, if we have the second element S12, that's the projection of S1 of t onto the basis function phi 2 of t. So we'll write that as S1 integral 0 to t S1 of t into phi 2 of t dt. So that's the projection of S1 of t onto the basis function phi 2 of t. Similarly, if we had a second signal S2 of t, in a two-dimensional space, for example, then the corresponding vector elements S21 and S22 can be written as such. So S21 will be the dot product of S2 of t onto phi 1 of t, and S22 will be the projection of S2 of t onto the basis function phi 2 of t dt. So we have seen what do these elements of the vectors represent. So basically each element of the vector representation of the signal is representing the projection of the signal onto the basis function. So we have n basis functions, so each element is the projection of that particular ith signal onto the corresponding basis function. The first element is the projection of the signal on the first basis function, the second element is the projection of the signal on the second basis function, and so on up to the nth element is the projection of the signal onto the nth basis function. Okay, so we have depicted here. So basically with this now we can represent each of these signals. So that's signal S1 of t can be represented as a vector consisting of these elements S11 and S12. Similarly, S2 of t can be represented as a vector consisting of elements S21, S22, and basically I'm just restricting myself here to a two-dimensional space, so representing the signal in a two-dimensional space consisting of only two basis functions, which are phi 1 of t and phi 2 of t, so that I can depict it on my screen. Okay, so basically if I had the signal S1 of t, so let me draw a separating line here. So if I have instead of Si of t, I put I equal to 1 now, so that gives us S1 of t. We can represent that as a vector S1, and that will be a vector consisting of two elements, S11 and S12. So because I'm just giving you an example for a signal that is represented in a two-dimensional space. So S11 and S12, that is S11 and S12. Okay, so we have our signal S1 of t represented as a vector in a two-dimensional space, and similarly we can depict or represent S2 of t as a vector S2 as a two-dimensional vector S21, S22, where these values for S11 and S12, S21 and S22 are given by these equations. So we have we're trying to represent these signals as projections as in a geometric way, rather than seeing them as simple functions of time. We are trying to look at these signals as in a geometric way, and that helps us to do a lot of things to understand the signals and the behavior better, okay, as we will see later on. But first let us focus on how to get this representation done, and later on we'll see how we can use this representation to analyze signals as well as the processes that happen in a communication system. Okay, so we are basically now representing the signals as vectors, and the size or length of the vector depends on the dimensions of the space in which it is represented. Okay, so I'm just giving here example for a two-dimensional space. So each signal is represented as a vector in a two-dimensional space here, and what are the elements of those vectors is given by these equations, but is nothing but the projection of the signal onto the basis functions phi j of t. I will now represent these as vectors, okay, and illustrate on a graph how these are represented as vectors and what do we mean by the projections. Okay, so I've talked about projections and I've given the equations to compute the projections, but graphically, what do we mean by projection? I will illustrate that to you in just a bit now. So what we have here is two signals, S1 of t and S2 of t. So okay, this line here, I'm going to denote that as S1 of t in its vector form S1, and this is basically S2 of t in its vector form S2. Now because it's two-dimensional space like the x-axis and y-axis, so each of these points here will be given by a coordinate of the x-axis and a coordinate of the y-axis, right? The x-coordinate and the y-coordinate. So that gives us the vector representation. So that's S11, S12 is basically the x-axis coordinate and the y-axis coordinate. Similarly, for this S21 and S22 is the x-axis coordinate and y-axis coordinate respectively, right? So the axes themselves are the basis functions. So we will call this axis as phi1 of t, and this axis as phi2 of t. And we'll call this as our signal S1 and this as our signal S2. So we have our two signals S1 and S2, and basically we are trying to represent them as vectors in this two-dimensional space. So I'll mark these points here. So each of these points over here are going to depict. So this point here is nothing but S11 comma S12. That's the x coordinate and y coordinate, right? Similarly here, this point here for the second signal is S21 comma S22, right? So that's the x and y coordinates of those points. Now we are representing our signals as vectors. So S1 of t, so I'll write it here, S1 of t is S1 depicted as S11, S12, and similarly S2 of t is S2 as a vector, and the elements of that vector are S21 and S22, right? So what are these S11 and S12, S21 and S22? Clearly, S11 is the x-coordinate of this point. So that's nothing but the corresponding x-axis value which falls here, right? So basically what we're saying is this projection here, okay? So that is basically called as S11. This value is S11. So the x-axis coordinate, or in other words, the projection of this vector onto the x-axis. That is, if we look at this signal from the top, it will fall on this line up to this length on the x-axis. So if we project, so if we throw light, a source of light from the top here, the shadow of this line will fall on phi1 of t up to this length, right? So that is basically saying S1 is projected onto the basis function phi1 of t. So that is what we mean by projection. So this here is this point here is the projection of S1 onto the basis function phi1 of t, which is S11, and S11 is defined as in this way. So it's a projection of S1 of t onto the basis function phi1 of t. Similarly, the projection of S1 of t onto the basis function phi2 of t, that will give us the value for S12. So if we are going to shine light from this direction, the shadow of this line will fall on the y-axis, which is the axis for phi2 of t, exactly till this point, right? So that will be the projection of S1 of t onto phi2 of t, which we will call as S12. So that's basically the y coordinate value for that particular point. So basically projection means if you are looking from the top or shining light from the top, what is the shadow of this line going to fall on, the length of the shadow on the y-axis, on the x-axis. That is the projection of the signal on phi1 of t. Similarly, if there is light from this side, from the right here, the shadow of this line will fall on the vertical axis, and its length is going to be like this, right? So that the projection value, that will be called as S2 of t, okay? S12, that is the projection of S1 of t onto the basis function phi2 of t, which is this element, okay? So similarly, we can find the projections of S2 of t onto the basis functions phi1 and phi2. So the projection of S2 onto phi1 is going to be this line over here. So from here, if we project this vertically downwards, it comes here onto the x-axis, which is the axis of phi1 of t. So that's projecting S2 onto phi1. So it's S21. Similarly, the projection of S2 onto phi2 is going to be over here. So that's S22. Right? The projection of S2 onto phi2 of t. So this is what we mean by projections, and this is basically the geometric representation of the signals S1 of t and S2 of t. So we have the basis functions phi1 and phi2. Again, I've written them as phi1 of t and phi2 of t. For conciseness, you can simply write them as phi1 and phi2, but where you need to write it as phi1 of t and phi2 of t, you can write it as that as well when you're doing the integration here to compute these elements. Okay, so basically we have now seen how to represent these signals in a geometric way as vectors, and what are the elements of these vectors actually representing geometrically. So using these elements, we can represent our signals in terms of the vector elements and the basis functions. As we have seen earlier in one of the equations, we have depicted our signal Si of t as a summation of these products, right? The projection of the signal onto phi1 of t into the phi1 of into the basis function, and we keep adding all those to get our signal. Okay, and that's basically saying that if we know these elements, we can synthesize or construct our signal using these projection values, using these geometric terms. So if we know the projections and if we know what are the axes of the functions that are representing the axis, we can construct our signal using those, right? So we'll use this equation and try to make a diagram to represent this equation. So that is called as the synthesizer diagram, or in other words, how to synthesize the signal Si of t from the values of the vector elements and the basis functions. So let's write down this equation one more time in the current slide. So we can write our signal Si of t as the summation of Sij into phi j of t for j equals 1 to n, and we can do it for I equals 1 to m. Okay, and n is going to be less than or equal to m. Okay, so the number of basis functions can be at most the number of signals. So if you have 5 signals, the number of basis functions will be at most 5, or maybe we can represent the 5 signals in a 3-dimensional space, because maybe all the 5 signals fall in a 3-dimensional space, but we cannot have 5 signals in a 6-dimensional space. Okay, so for 5 signals, 5 dimensions would be sufficient. So okay, we have now this equation, which was called as the synthesizer equation for the signal based on their geometric representation elements. So we have this Sij, which are these vector elements, and these phi j's are the axis functions, okay, which are the basis functions. So using these, we can synthesize our signal Si of t, and we can make this diagram. So basically it's S, for example, if I want to synthesize the signal the Si of t, it's Si1 phi1 of t plus Si2 phi2 of t plus Si3 phi3 of t plus and so on. So we can make a diagram for this equation, a block diagram that depicts the functionality of this equation, and we will see how it represents the synthesis of the signal Si of t. So this is what our synthesizer diagram is going to look like. Okay, basically we're going to synthesize this equation. Okay, this is the same equation which we had here in a short form where we did the summation Sij phi j of t, and I just opened that up. Okay, Sij Si1 phi 1 plus Si2 phi 2 and up to Sin phi n of t. So basically we are taking each of these vector elements Si1 and multiplying it with the corresponding basis function. So the first element here, or the first branch here, is going to take in as input Si1 and multiply with another input phi 1 of t. So we'll have Si1 and we'll have another arrow here. So let me make those arrows for the inputs, which will be the basis functions. So this input here will be phi 1 of t. So these two are going to get multiplied, Si1 into phi 1 of t. So this here is going to be a multiplier. Similarly, here we'll have Si2 multiplying phi 2 of t. So that's a product here, and like this we'll have n such things. Okay, like this we'll have the third branch for Si3 into phi 3 of t up to the final branch, which will multiply Si, and that's the nth branch, and the input here will be phi n of t. And these products, okay, each of these products are getting added together. That's Si1 phi 1 of t plus Si2 phi 2 of t plus up to Sin phi n of t. So all of these are going to get added here. So that's basically our summation, and what we get at the output of the summation is our signal Si of t. So that's Si of t. And basically what we are trying to see here is that we can use this equation or this block diagram to synthesize our signal, that is to construct Si of t, the signal Si of t, using the vector elements Si1, Si2, Sin, and the basis functions phi 1 of t, phi 2 of t, and so on. So this is basically the synthesizer block diagram for synthesizing a signal from its geometric representation terms. So we call this as a synthesizer. Okay, and just as we have the synthesizer, we can do the reverse process of breaking up the signal. So if we have the signal Si of t as our input, how do we get back these elements of the vector? Okay, the vector elements S11, S12, and so on. So that's basically the second equation here. So we take S1 of t, multiply it with the basis function, and integrate from 0 to d. That is basically computing the projection of the signal onto each of the basis functions. That will give us the corresponding vector element Si1, Si2. So the reverse process, okay, going from Si of t to these vector elements Si1, Si2, that is called as the analyzer. So this process is called as a synthesizer. And we will now look at the block diagram for the analyzer, which analyzes the signal Si of t and gives us the vector elements Si1, Si2, and so on. So the process of analyzing or going in the reverse direction, that is from the signal to get back its vector elements, okay, we can get it in this way. Okay, so we start off with the signal. So we'll have the signal going as input, as a common input to all these parallel branches. So the input here is our signal Si of t, and this signal is going to be multiplied with each of the basis functions. So we'll multiply the signal with phi 1 of t in the first branch, with phi 2 of t in the second branch, and so on and so forth up to the nth branch, where we'll multiply with phi n of t. So each of these circles here is denoting multiplication, because we are multiplying the signal with the corresponding basis function. So Si of t into phi 1 of t, and that product will get integrated from 0 to t. So after multiplying, we integrate that from 0 to t, so that should give us SI1. So the integral 0 to t Si of t into phi 1 of t is Si1. That's exactly the equation that we saw earlier here. So S11 is integral S1 of t into phi 1 of t. So if it's Si1 is Si of t into phi 1 of t. Si in general, any Sij is Si of t into phi j of t integrated from 0 to t, and that is exactly what we are depicting here. So Si1 is integral Si of t into phi 1 of t from 0 to t, right? So when we integrate, we get Si1. Similarly, the second branch is multiplying Si of t with phi 2 of t, and that product is going to be integrated from 0 to t, and that will give us Si2. Similarly, integrating the nth branch from 0 to t will give us Sin. Okay, so basically we are doing the analysis here of getting the values of the vector elements of the signal. So in general, it's Sij is the projection of the signal Si of t onto the basis function phi j of t dt, and that's 0 to t, right? And that is exactly what we have depicted here to get each of the elements. So the projection on the basis function phi 1 gives Si1. The projection on the basis function phi 2 gives the second element Si2. And like that we can do for all the signals. The second signal S2 of t, the third signal S3 of t. So I goes from 1 to m, and this j goes from 1 to n, and that way we can compute the vector elements of each of the signals. Okay, and this process is called as analyzing the signal Si of t and getting its vector components or vector elements. So we call this diagram as an analyzer. Okay, so this block diagram is depicting the analyzer, just as the previous one was depicting the synthesizer equation. So this equation is the synthesizer equation, where we can synthesize our signal using the vector elements and the basis functions, and the opposite, which is to split the signal into the vector elements using the signal and the basis functions. That is called as the analysis, and the block diagram that is depicting the process is called as the analyzer, and the corresponding equation here is called as the analysis equation or analyzer equation. Okay, so we have seen these two depictions here. Again, so far I have not even gone into how to find this phi 1 of t and phi 2 of t. Okay, we'll come to that later, but let's get the concept going first as to what exactly we're trying to do, and then we'll see how to do that. Now, before we go further into this, I want to introduce a few more terminology, and I'm going to use some basic concepts from your undergraduate or maybe even from high school topics, and I want to extend those ideas to our signal representation in a geometric way. And the first such definition that we are going to introduce now is called as the norm of a signal, or the norm of a vector. Okay, and we also want to see how we can compute the energy of a signal from its vector elements, right? So we have defined earlier the energy of the signal. Let me go back. Okay, so we defined the equation for energy, right, as integral 0 to t the signal square of t, right? So we did this for the basis function. Similarly, if we want to find the energy of any signal s of t, it will be integral s square of t dt, right? And that will give, whatever is the answer, that will give us the energy of the signal. Now, if we have the signal represented in the vector form as this, rather than having the signal as a time domain as a function of time, how can we compute the energy from this vector? And similarly, how can we compute the length of the vector and so on? And once we have two signals in represented in a vector form, how do we compute the distance between those two signals? Okay, now when I introduce the term distance, immediately it should ring bells that how this concept of representing signals as vectors in a multidimensional space is going to help us in a communication system, right? So in a communication system, we are dealing with the process of separating different signals. We have to separate the desired signal from the unwanted signal. So if we have some distance between the signals, we can separate them. If the signals are too close to each other, we may not be able to separate the signals, right, the desired signal from the undesired one. So what I'm going to introduce now is what is called as the norm of the signal, which is basically the length of the signal. And then we will also talk about the distance between two signals. And the third thing we are going to do is how to compute the energy of a signal which is available to us in a vector form rather than as a function of time. Okay, so we're going to see these three things, and we're going to do that using our basic understanding of geometry. So to do that, I'm just going to take one signal which in a two-dimensional space. So I'm going to represent this signal S1 of t, S1 of t as its vector equivalent S1, and it's in a two-dimensional space. So I'll have S11 and S12. Okay, so in a two-dimensional space, we have two basis functions. That's phi1 of t and that's phi2 of t. Okay, so that's a two-dimensional space with two basis functions, phi1 and phi2. Now the projection of this signal S1 onto the basis function phi1, that gives us the value S11. Okay, so if we project it down here, that's the x coordinate or the coordinate of phi1 axis. So that's our S11. And the corresponding projection onto the second basis function, that is on the y-axis, which is phi2 of t, that projection is S12. And that is our representation of the signal in the graph. Now what we are interested in is to determine the length of this vector. Okay, we call that as the norm of the signal S1. So and let me write that down. It's called as the norm of S1 and is denoted as, we denote the norm with two lines. So norm of S1 is S1 written in two pairs of lines. Okay, so you have these two-line notation that represents the norm of the signal S1. Okay, now since we have the signal in a geometric way with the projection values S1, we can find the length of this line, which is the norm of S1. So let me write that here. So the length here is norm of S1. Similarly, we can find the length for any signal, and we can use the Pythagoras theorem to compute the length of this. So this is a right angle triangle here. So that's the right angle here. So that's 90 degrees. So with the right angle triangle, we can compute the this length using the length of this and this. Okay, so S11 is this length, and the height here is S12. Okay, that's the height of this line. So we can compute the norm as S11 square plus S12 square by applying Pythagoras theorem. So from this figure, we can write the norm of S1 to be equal to, from the Pythagoras theorem, we can write it as the square root of S11 square plus S12 square. Okay, so that's the length of the line. So hypotenuse square is equal to the adjacent square plus the opposite square, right? So since the hypotenuse is not squared now, so we take the square root, right? So we have this representation for the norm of the vector. So once we have the signal represented in terms of the vector, we can now compute the length of that vector as using these elements. So S11 square plus S12 square under the root. And that's for a two-dimensional case. So in general, for an n-dimensional case, if we have a vector of length n, we just add those additional terms inside this root, right? So for an n-dimensional vector in an n-dimensional space, okay, so in an n-dimensional space, then that means the signal S1, that is the signal S1, okay, I'm just using one signal here, S1 will be an n-dimensional vector as S11, S12, let me write the two clearly, S12 and so on up to S1n. So that's an n-dimensional vector. In this case, the norm of S1 is equal to S11 square plus S12 square plus S13 square plus so on and so forth up to plus S1n square, and all these terms are under the root, okay? And so that's basically, we are just going to square each of these elements, add them together and take the square root. That gives us the norm of that signal vector S1. Similarly for S2, whatever is the signal, the vector elements, it will be for S2, it will be S21 square plus S22 square plus S23 square up to S2n square under the root, right? So that is basically our representation for the norm of the vector, or in other words, we can write this more compactly. This equation for the norm, we can write this more compactly for any signal Si of t represented by its vector Si. So in general, we'll write the norm of Si as the summation of Sij square for j going from 1 to n, and this whole thing is going to be under the root, okay? So under the root means power half, okay? The square root means it's to the power 1 by 2. So that is the general notation to the general equation for computing the norm of any signal Si of t when that signal is available as a vector form, okay? So that's when Si of t is available as a vector Si, which is given as Si1, Si2 and so on up to Sin, okay? So when we have this vector, then we can compute the norm in this way, okay? So that's the that's the process to find the length of the signal based on its vector elements. Now we want to see how to compute the energy of the signal based on its vector elements, okay? We saw previously the general equation to find the energy is just integrating the squared function of time, and that gives us the energy. But in vector terms, we will see how to compute the energy now. So if we denote the energy of any particular signal Si of t as Ei, so for S1 of t it's E1, for S2 of t it's E2 and so on. So the equation to find the energy is integral 0 to t Si square of t dt. So that's our equation to find the energy if we know the time domain function Si of t. But if we have this signal available to us as a vector, so suppose we have Si of t as a vector Si, which is given to us as elements of vector Si1, Si2 and so on up to Sin, okay? Then how do we compute the energy? So what we will do is we will simply split this equation and write it as integral 0 to t si of t into si of t dt, right? And let me make this separation here for this representation. Okay, so that's our I've just broken the square as SI into SI. Now each of these signals can be represented in terms of their basis functions as the vector elements, right? So if we look at the synthesis equation, that is, so if you go here, so we have the synthesis equation which says any Si of t is Sij summation Sij into phi j of t. So we are just going to write that each Si of t in the synthesis form. So we can write this as integral 0 to t. The first Si of t is summation Sij into phi j of t, and j goes from 1 to n, j equals 1 to n. So that's the first Si of t. Similarly, the second Si of t, which is multiplying there, that will be another summation. So that will be summation. Now because we have used the summation, the variable j here, going from 1 to n, rather than using the same variable, we'll use a different variable. So we'll call it k equals 1 to n, and it will be Sik into phi k of t dt. So that's Si of t written 2 times, and then we have this dt, right? So that dt is common to that product. So we'll have this whole thing in the bracket here, okay? With that we'll have that dt, and this whole thing is integrated with respect to t, okay? Now we just play around with this and rearrange these terms, and we will see what happens. So what we'll do is, since these Sij and Sik, these terms are are not functions of time, we can take them outside the integral. So we can take these summations outside the integral and keep only the functions of time inside the integral. So we'll have it as summation j equals 1 to n Sij into summation k equals 1 to n Sik into the integral 0 to t phi j of t into phi k of t dt. So only the time dependent functions are kept inside the integral. All the others have been taken out of the integral. So now we have these terms. Now what happens is, because of the property of the basis functions that their dot product is 0 if they are different, right? So phi j into phi k integrated from 0 to t should be 0 if j is not equal to k. And if j equal to k, because they are orthonormal basis functions, that gives the if j is equal to k, it will become phi j square, and that integral should evaluate to 1. So basically what is going to happen now is, this integral is going to be either 0 or 1 depending on whether j and k are same or not. So we'll have this integral as equal to 0 if j is not equal to k, and that's going to be equal to 1 if j is equal to k. So if j is equal to k, it's 1. If j is not equal to k, it's going to be 0. So when j and k are different, this whole thing, this integral becomes 0, and 0 into any of this is 0. So we don't need to worry about the case for j not equal to k, because this entire equation here becomes 0. Now if j is equal to k, then we can replace the j and k and make it as the same j. So when j is equal to k, that's when this integral is equal to 1 and non-zero. So we need to worry about only that case when j is equal to k. So under this condition, what will happen is the integral becomes 0 when j is not equal to k, and it's equal to 1 only when j is equal to k. So we can make the j and k to be the same in this case. So that will become integral j equal to 1 to n Sij into summation again j equal to 1 to n Sij. So that will simply be equal to that will become equal to summation j equals 1 to n Sij square. So what we notice here is that the energy of the signal can be computed from its vector elements as simply the sum of the square of these vector elements. So it's SI1 square plus SI2 square plus SI3 square up to plus SIN square. So that's the summation here. Now if you notice, and if you compare this with the previous summation that we calculated for the norm of the signal, you see that the norm is the same thing, summation Sij square, but it's under the root, right? So it's power half. So basically the energy is the square of the norm. Okay, so let's write those two equations and get the relationship between the energy and the norm of the signal. So what we have here is the energy of the signal EI when you have the signal as a vector representation is basically the summation Sij square, which is going from for j equal to 1 to n, and we had the norm of Si as as the summation Sij square for j equal to 1 to n, but it's power half. Okay, it was under the root, so it's power half. So comparing these two equations, we can now say that the energy EI is equal to the square of the norm of Si. Okay. So the relationship between energy and norm is that energy is equal to the square of the norm, or the norm is the square root of energy. So we say energy of the signal is equal to square of norm. Okay, so now we have this relationship between energy and norm. So we have seen how to compute the energy from the vector notation of the signal, and how to compute the length of the signal, which is nothing but the norm of the signal. And then we will also see now what do we mean by this energy computation, right? This is Sij square. It's basically we are multiplying the signal vector with its transpose. So when we have this signal as a vector here, now Sij square, so we want to multiply each element and square it and add it, right? So the implementation representation of that is going to be, so if we have our signal denoted as Si, I'll write it as a vector form. So simply Si is Si1, Si2, and so on up to Sin. Okay, so that's a vector of length n, and if you want to compute the energy, it's Sij square added together. So we basically square all these terms and add them together, that is, add those squares. So the way of doing that is, let me make a separating line here. So if you want to compute the energy EI, it is basically multiplying Si transpose with Si, and that will give us exactly this representation, okay, which is summation Sij square. And that's basically, the transpose means making the column as a row and row as column, right? So because this vector is defined as a column vector, the transpose will be a row vector. So that will become as a row, we have to, the transpose is a row vector, so that will be Si1, Si2, and so on up to Sin. So that's a row vector. multiplied with the original SI, which is a column vector. So that will be SI1, SI2 up to SIN. So that's our column vector. So when we multiply these two, it will be this into this plus the second element into the second element here plus the third element into the third element here plus the fourth element into the fourth element here, and so on up to the nth element, right? So that will basically give us the energy, which is equal to SI1 square plus SI2 square plus SI3 square plus and so on plus SIN square, right? So that is basically summation Sij square for j equals 1 to n. Okay, so that's our equation for energy. Okay, and I'm just going to make a separation here so you're not confused, right? So we have seen how to compute the energy now in terms of the vector elements, and that is basically equal to the square of the norm. Okay, that is equal to the SI square, the square of the norm. Okay, that's SI square. So that's what we have here. Or basically what we are in other words saying is the energy of the signal is nothing but the dot product of the signal with itself. So SI transpose into SI is the dot product of the signal with itself. Now likewise we can compute the dot product of the signal with another signal. So if we have SI transpose into SJ, then we will have the dot product of two signals SI and SJ, and that will give us an indication as to what is the angle between those two signals. Because if the dot product is 0, then the angle between the two signals is 90 degrees. That means the signals are orthogonal to each other. So we can compute the dot product of two signals in a similar way. So as I said, we can compute the dot product of two signals, SI of t and SK of t, just as we computed the dot product of SI of t with itself, which gave us the energy of the signal. So the dot product between SI and SK is integral 0 to t SI of t into SK of t dt, and we can compute the dot product in terms of the vectors as SI transpose multiplied with SK, where SI and SK are the vector representations of the signal. So where SI is the vector of the signal SI, so that's SI1, SI2 up to SIN. So that's an n-dimensional vector, and SK is also an n-dimensional vector representing the signal SK. So that will be SK1, SK2 and so on up to SKN. So the dot product of these two can be obtained by taking the transpose of this vector. That means writing this as a row vector and keeping this as a column, and that will give us the dot product of those two signals. So in other words, we can write the dot product as integral 0 to t SI of t into SK of t dt, which is SI transpose into SK, which is nothing but SI transpose is the SI vector represented as a row vector. So that's SI1, SI2 and so on up to SIN, and SK will be the vector representing SK. That will be SK1, SK2 and so on up to SKN. Okay, so we have the vector representation, and using the vector representation we have computed the dot product of these two vectors. The next thing we can do is the computation of the distance between these two vectors. Again, we are going to use the idea of our basic geometry, where we compute in a two-dimensional space, where we can get the distance between 2 points by using their coordinates, right? So let me depict that. So the next thing we are going to do is to compute the distance between two signals. So if we represent one signal as a vector s1 and another signal as a vector s2, then the coordinates of this point is the x-axis and y-axis values, right? So x1 y1 and x2 y2, which is basically s11 s12 and s21 s22, right? So the coordinates would be for this, so if this is our phi 1 of t and this is phi 2 of t, then we'll have the coordinates as s11 comma s12, and for the second signal it is s21 comma s22. So that will be the coordinates of the points which are representing the signal s. I'm just doing the example for a two dimension. This, or basically we can say this as x1 y1 and x2 y2, right? And we want to compute the distance between these two signals. So to compute the distance, okay, let me mark this line as the distance between the 2 points. So that distance is what we want to compute now, so d. So if we call this as x1 comma y1 and this as our point x2 comma y2, then from basic geometry we can write this distance d. So let me write that inside the line so that it's clear. So the distance d from basic geometry can be written as d is equal to x1 minus x2 the whole square plus y1 minus y2 the whole square, and that's under the root, right? So that's from basic geometry, right? The distance between 2 points when we have the coordinates of those points. So likewise, these elements of the vectors are basically representing the coordinates. So if it's in a two-dimensional space, we can write the distance between these two signals s1 and s2 as in terms of their vector elements s11 and s22. So the x1 here is s11 and y1 is s12, and the corresponding x2 and y2 are s21 and s22 respectively. So the distance between these two signals can be represented as so we can write this distance d as s11 minus s21 the whole square plus s12 minus s22 the whole square, and that's going to be under the root. Okay, so that's the basic way of finding the distance between the two signals. And we can extend this idea if we have the signals as n-dimensional vectors rather than just 2 dimensions. So I've depicted here for 2 dimensions, and based on the 2 dimensions we can extend this idea to have multiple dimensions as well. So if we had instead of s11 and s12 only, if we had s13, s14 up to s1n, we can simply compute the distance d in general. So in general we can write it as, so in general we can write that distance as d equals the summation, because there is an addition term here, okay, like this we can keep adding. So it's s11 minus s21, s12 minus s22, and so on. So for 2 signals, the distance between 2 signals, so in general it will be summation Sij minus Skj the whole square for j equals 1 to n. Okay, so that's basically extending the distance equation for in the 2-point form to a vector of any length. If we have the signal represented in multiple dimensions, 3 dimensions or 4 dimensions, or in general n dimensions, then the general expression for the distance will be given by the square of this. So we'll see, and we need to take the square root. Okay, we need to put this under the root to get the distance, but because I don't have the space here to put the root, I'll just write this as this is equal to d square, right? So if you want the distance, you'll have to take the square root of this, so the whole thing power half if we remove the square here, right? So that in this way we can compute the distance between two signals, or we can in general write this as the distance between two signals Si of t and Sk of t is given as the integral from 0 to t of the difference of those two signals squared, right? So that will be the distance squared basically. So Si of t minus Sk of t dt, and because we are writing the distance squared now, so that's in terms of the square, that's basically equal to what we wrote here for the distance square. Okay, so that's going to be equal to this term, so that will be summation Sij minus Skj the whole square for j equals 1 to n, and that is basically the square of the norm of the difference of the two signals, right? So summation of this is nothing but the norms squared, right? So if you go back to the definition for the norm of the signal, we saw that the norm of the signal is Sij square power half, right? So when we don't have this half, it is basically norm squared, and instead of Sij square we have the difference there, right? So what we have here is Sij minus Skj the whole square, so that's basically the square of the norm of the difference of the two signals. So that is norm Si minus Sk the whole square. Okay, it's the square of the norm, and since the norm is the length, the square of the norm is the square of the length, and now we have the norm of the difference of the two signals, so that is nothing but the norm of the distance between the two signals, which is d square. Okay, and that is exactly what we have depicted here. Okay, and we have basically used the basic ideas of geometry when we have a signal represented as when you know the coordinates of the points, we can find the distance between those 2 points using this. Okay, and we just replace x1 and y1 and x2 and y2 with the corresponding projections. Okay, s11 and s21 correspondingly s22 and s12, right, for x2 and y2. So that's for y1 and y2, that is. Okay, so by doing that we have now obtained an expression for the distance between the two signals Si and K, and basically we have this squared. If we take the square root of this value, we'll get the distance. So this is basically the square of the distance, or in other words, if we take the norm of the difference Si minus Sk is the distance between the signals Si and Sk. Okay, so you can now try to appreciate why we are doing this representation of signals in a geometric form. It's because it makes things makes the analysis much more simpler, because we can use the elementary ideas of geometry to find the distance between the two signals and how to separate the signals to compute its energy. So all the computations become much easier if we are able to represent the signals in a geometric form, and it's easier to visualize them as well as to where they lie in the space and what is the distance between them, and how easy or difficult it's going to be to separate the signals from each other and so on. So that's the idea behind representing the signals in the form of vectors in a geometric space. Or that's the whole point of representing the signals, having the geometric representation of the signals. Okay, so far we have seen the norm of the signal, the energy of the signal, and also to the way of computing the distance between two signals when we have them in a geometric form. We have not seen so far still how to compute the basis functions themselves. We will come to that later. But we've got one more thing to do, which I will cover in the next lecture, and that is to find the angle between the two signals. Okay, so far we have done up to the computation of the distance between two signals, and likewise we can compute the angle between two signals. So if we have two signals like this, so if this is our S1 and the other one is S2, so let me write that. So this is our signal S1 and that's our signal S2. There is some angle between those two signals. Okay, we can call that angle theta, right? So how to compute the angle between two signals, and how we can get that angle in terms of the vector elements. Okay, so we will see all of that in the next lecture, and we will go further in the next lecture into how to compute the basis functions, that is how to compute phi 1 of t, phi 2 of t, and so on. Okay, so I'll stop here for this video. We'll continue in the next lecture.